And we saw that clock processes are sums of random variables. So the first question to ask ourselves is, what type of limit can we expect to get? Because this is well known in classical probability theory. So today we will study the REM-like trap model. And in order to do this, we will first ask ourselves what are the possible limits in classical probability theory for sums of independent random variables, because the trap model is, the clock in the trap model is a sum of independent random variable. So the talk will be in two parts. The first one will be about basic convergence theorems for sums of independent random variables, and in the second part we will apply it to the study of the clock process of the REM-like trap model. So I let Z and I be an array of IID positive random variables on a probability space that I'll call omega fp. And given two sequences, AN and CN, I'll let Sn be the partial sum process that assigns to T the sum from I equals 1 to integer part of A and T of the scaled variable Zni over Cn. So this is a partial sum process on our plus. And we are interested in the possible limit this object can have when n goes to infinity. So clearly, if the sequence Sn converges, then it must have independent and stationary increments, because we have here a sum of IID random variables. So it should be a Levy process, because stochastic processes that are homogeneous with independent and stationary increments are Levy processes. But we also see that if the limit exists, the path must be increasing, because the z's are positive random variables. So among the class of Levy processes, it should be a subordinator. Now we know by Ito's representation of subordinators that they are completely determined by two components. The first is a drift, and the second is a Poisson point process. So let me give you Ito's representation of subordinators. So for any process, Levy process, X and T with increasing path, can be, so any Levy process with increasing path can be represented as, there's no n here, as the sum of a drift, a linear path, plus the sum over all k's, such that tk is smaller than t of psi k, where A is positive, and the points tk psi k are the points of a Poisson point process. Poisson point process, PPP, of, Levy measure d nu times dt. So what is d nu? It is the Levy measure of our process. So any Levy process, I would say, with Levy triple A0 nu can be represented, that has increasing path, can be represented in this way. So we know that a Cadillac function is the sum, can always be decomposed into the sum of a continuous part plus a jump part. So here we see that the continuous part is this drift, and the jump part is given by the points of this Poisson point process, where tk gives us the times at which the jumps occur, and psi k gives us the size of the jumps. Levy process is always determined by its Levy triple. So A is the drift constant. The second component is the Wiener process, but in subordinators, the Wiener component is always 0. And the third component is the Levy measure, and the Levy measure gives us the intensity measure. So I wrote it the other way around. It's dt, d nu. Is the intensity measure of our point process. Okay. So now that we have this representation, the idea is, in order to prove convergence of Sn, we will first identify an underlying point process and prove that this point process converges to a Poisson point process, and then use this to sum the points of the point process and get convergence of Sn. So this is the strategy that we will apply to prove this convergence. So the first step is convergence of the induced point process. So how to identify this induced point process is simple. I will form the point process whose points have abscissa the time, so I over an, and ordinates, the scaled increments z and I over cn. So the sum here is over all i's. So this here highlights the role of our two sequences. This an is the time, so this process records the time on scale an at which the large increments z and I over cn are attained. So questions about the convergence of this point measure can be reduced to questions on the time-varying dependence of the set of increments of our sum. So now there is a famous, well-known theorem about extreme value theory that tells us the following. So let n be a Poisson point process with intensity measure nu. Then the sequence Nn converges weakly to this point process n if and only if the following condition is satisfied: an times the probability that Zni is larger than uCn converges to the tail of the measure nu for all u positive. So this convergence is weak convergence in the space of point measures on 0 infinity times 0 infinity. So let me just say 2 words about this. I wrote a little appendix about about point measures and convergence of point measures. So just to refresh your mind about this is a delta mass at x, at some point x. A point measure is a sum of delta masses at a sequence of points xi. If you now take this xi random variables, as we do it here in this construction, what you get is a random variable that is a mapping from the probability space of your random variables here into the space of point measures. And this space of point measure, you then equip with a sigma algebra that makes all subsets of point measures measurable. And you also must equip it with a topology, because we are interested in taking limits, and to give meaning to taking limits, you need to do that. Now, the topology we will use in the space MP of point measures is the vague topology. The vague topology is a very strong notion of convergence, because it will imply that the points in the support of the point process converges. So we take any sequence of points in the support, and they will converge to that sequence of points in the limit. Now, I explain how to do this in the appendix on point processes. And if you don't know this, you can just read it. So we see that the condition for the convergence of our point process is a condition about the tail behavior of our random variables. There is a nice connection with this condition and the theory of regular variations. So let me just mention it as a little lemma. So suppose that we have 2 sequences, A tilde n and C tilde n, that diverges, and that are such that A tilde n over A tilde n plus 1 goes to 1. Then for any monotone function u, the quantity A tilde n u of C tilde x converges as n diverges to a limit Vx, if and only if u is a regularly varying function is regularly varying at infinity with some exponent, say rho, in R. And in this case, Vx is equal to x to the power rho times a constant, say V1. So this tells us 2 things. The first is that this condition we have here is clearly a sequential version of the regular variation condition, such a sequential version of the regular variation condition. And the second thing it tells us that is that we don't have much choice for the possible limit here in this case. Okay, so this is the case of monotone functions. There is a second connection between this condition, this regular variation condition, which is that the same condition appears when you want to establish the law of the extremes of a sum of random variables, of a sum of independent random variables. It is the same condition, this convergence condition, that you will need to establish that the maximum of a sum converges. So So now we will just apply this convergence to sum the points of our point process. So with convergence of sums, via this induced point process. So I will first take the case of IID random variables. Here I took IID sequences, so I would consider it an array. Now I want to specialize to the case of non-arrays. So ZNI is not a ZNI precisely, it's a ZI. RIID positive random variables. Okay, so for this, we have the following result. I don't want to write it again. Sn is always the normalized sum of the variable Zn. So here, Sn is defined in the same way, but with Zn replaced byZni, okay? So let S infinity be a stable subordinator. So let me come back 2 seconds to the definition of subordinators. A stable subordinator is a subclass of the subordinators. So the important word is stable. With Levy measure, nu of u infinity given by u to the minus alpha times a constant for some alpha in 0, 1. So this is a subclass of subordinators whose Levy measure takes this special form, u to the minus alpha times a constant, with some alpha in 0, 1. Alpha here is called the index, so a stable subordinator with index alpha. Then there exist sequences AN and CN such that as n diverges, the partial sum process, Sn, converges to S infinity if and only if the variables Z and I are in the domain of attraction of a stable law of index alpha. So this can be rephrased if and only if the probability that Zi is larger than u can be written in the form u to the minus alpha times L of u, where alpha is in 0, 1. And L of u is a slowly varying function at infinity. So L of ut divided by L of t goes to 1 as t goes to infinity. this convergence here is in the space of Cadillac path on 0, infinity. And it holds in the J1 topology of Gayrard in that space. So again, I don't have time to redefine everything about the topologies I use, but I wrote an appendix about this Gayrard topology. It is a topology in which the jumps converge. So unlike the M1 topology that merges jump in the limit, in this topology, each jump in the limit coincides to a converging jump in the converging sequence. And this is very important for us for applications to aging. So I want to explain how we prove the implication. So I will not do the if and only if, but the implication that if this condition is satisfied, then this convergence holds. So what do I want to keep? Yes. Well, I will rewrite it because it's not in a very good position. So some hints about the proof. So let us pick the sequences AN and CN such that AN times the probability that ZI is larger than CN is equal to 1. If I define my sequences in that way, then I see that this quantity can be rewritten. So the quantity AN times the probability that ZI is larger than CNU is equal to the probability that ZI is larger than CNU divided by, so AN is 1 over this, the probability that ZI is larger than CN. And because the Z's are in the domain of attraction of a stable law of exponent alpha, then this quantity converges to u to the minus alpha as n goes to infinity. So let me call this nu n of u infinity. And this gives us our limit, nu of u infinity. Now, by this theorem, we know that the sequence of point measures with points I over AN, ZI over CN, we know that it converges weakly in the space of point measures to a Poisson point process with points ck, psi k, an intensity measure, dt d nu. So now that we have this, what we want to do is use a continuous mapping theorem to sum the points of our point measure and reconstruct our partial sum process. So to do this, I will introduce a small truncation threshold. And so let me rewrite the process. It is the sum from I equals 1 to A and T of the increments Zn scaled by Cn. And I will rewrite this as the sum over all z's such that the increments are larger than delta plus the sum of the small increments, smaller than delta. So let me call S plus n delta this process, and the other part is S minus. Now the point of doing this is that the map that sums the ordinates of our point processes, so the map from the space of point measures to the space of Cadillac path that to a point measure with points tk, psi k. So I will call it T delta, assigns the sum of psi k's such that psi k is larger than delta. The sum is over all k such that tk is smaller than t. Then this map, you can check, is continuous. So I can apply a continuous mapping theorem, to deduce that as n goes to infinity, S plus delta converges. So it converges in the space D as n goes to infinity to S plus delta, where S plus delta is T delta of n. Now, by the ethos representation that I erased, we easily see that S plus delta converges locally uniformly in T to our desired limit, S infinity. So as delta goes to 0, as delta converges locally uniformly in T, and almost surely, this means for almost all realization of our point process. And from this, we deduce that S plus delta converges weakly to S infinity in D. So we are happy because we have our desired limit. Convergence, weak convergence in D for me is always convergence in G1. I will not always mention it, but it is the only topology that I will consider in these lectures. I will never talk about any other topology on cohort space than J1, so you cannot be confused. So we still have to prove that the sum of the small increments here will not contribute to the sum in the limit. So to do that, I will use a very classical criterion that I learned in Billingsley that tells us that if we have a sequence of random variables indexed by two parameters, n and delta, that converges to limit S infinity. So I know that S and delta converges. I know its limit, and I'm interested in knowing if Sn converges to the same limit. And we are on cohort space equipped with this weak topology. J1 topology. So I have a metric, which is scored metric on this space. And what Billingsley tells us is that if the probability that the distance between these two processes is larger than epsilon, goes to 0 as the lim sup of n goes to infinity and delta goes to 0. Then indeed we have that Sn converges to S infinity in D. So I only now have to check this condition. So let us do it. So you will see the definition of the metric rho infinity in the appendix, and we can easily convince ourselves that it is enough to check this for the metric rho 1, which means instead of doing it on the interval 0 infinity, we do it on any finite interval, but any finite interval, I can choose rho 1 for convenience. So this, I have to check that the distance in rho 1 is larger than epsilon, goes to 0. So now this is bounded above by the probability that the supremum for t in 0, 1 of the sum, so S n t minus S plus delta n t is larger than epsilon. Now, the difference appearing here is nothing else that the sum of the small increments. And so here I can drop the modulus, replace this by the sum of the small increments, and obviously the sup is bounded above by the value of this sum at t equals 1. So this is bounded above by the sum from 1 to an 1 of the increments zi cn minus 1, indicator set of zi cn minus 1 is smaller than delta, is larger than epsilon. So this is in the indicator set. So now to bound this, I will simply use a first order Chebyshev inequality. So this is smaller than epsilon minus 1 times the expectation of the sum from 1 to an of zi cn minus 1 indicator set of the truncation at delta. Okay, and now we know the law of z. So we know that z is in the domain of attraction of a stable law, so we can easily evaluate this expectation. To do this, you do an integration by part. So this here is bounded above. The sum simply becomes an because the variables are IID. So I get the expectation of z cn minus 1 indicator set of this truncation. You do an integration by part to get that this is bounded by the integral from 0 to delta of the probability that zi cn minus 1 is larger than u du. And now we are nearly done because an times the probability of the tail of the variable here, we saw converges to u to the minus alpha. So I would like to pass the limit n tends to infinity inside the integral and conclude that this is the integral of u to the minus alpha. I still need an argument to do this because, of course, I cannot push a limit inside an integral without an argument. But here, this is simple because this is a sequence of monotonous functions that have a continuous limit. And we know that these functions are locally uniform. So I can push the limit inside the integral, and I get that the limit as n goes to infinity of this quantity is bounded above by epsilon minus 1, the integral from 0 to delta of u to the minus alpha du. And this is u to the 1 minus alpha over 1 minus alpha, evaluated at delta. And since alpha is smaller than 1, this goes to 0 as delta goes to 0. So we get that this is 0. So I wanted to show you this proof in detail because this is the pattern of proof that we will use all the time. So we see that we, in fact, obtain two conditions for the partial sum process Sn to converge. So this partial sum to converge. The first condition is a regular variation condition on the tail of the increments of the sum. And the second condition is this condition here, that the sum of the small jumps in the limit do not contribute to the sum. So the morale of this story is that in this case, when your variables z and I, zi are in the domain of attraction of stable laws, the sum in the limit is not dominated by the very large number of the very tiny jumps as it is in the law of large number type of limit, but here it is dominated by the very small number of very large increments, so it is dominated by the extreme events in your sum. And this is what we will be interested in, and this is the pattern of proof that we will develop in the rest of the talk. So in the case of independent random variables, things are well known. In the case of arrays of variables, let me just quickly tell you the theorem we have. So theorem. So this is for arrays. So let Z and I be an array of IID positive random variables. So why am I interested in arrays? It is because for us it is important that the law of the random variable is allowed to be depending on the parameter, an extra parameter in the process. For us in statistical mechanics, it is the size of the system. So it is really important to have results for arrays of random variables. And so again, Sn is the sum. I will not write it. So let S infinity be a subordinator with Levy triple 0, 0, mu, and a Levy measure mu on 0 infinity, satisfying that the integral of the infimum of 1 and x, d nu x, is finite. So if there exists sequences an and cn such that, so two conditions. The first is an times the tail distribution of the scaled variable Zni over Cn converges to the tail of the Levy measure nu for all u positive. And so as n goes to infinity. And the limit, so this is our earlier condition on the small jump, the limit as delta goes to 0, lim sup as n goes to infinity of the expected value of Cn minus 1 Zn I, the indicator function of this quantity is smaller than delta, goes to 0. Then if the sequences an and Cn are chosen such that these two conditions are satisfied, then the process Sn converges to our subordinator with this Levy measure to S infinity. So we remark here that two things. I do not have an if and only if condition, but I don't really care about this, but because what I want is really sufficient conditions for my partial sum process to converge. So I'm happy to have only sufficient conditions. The only thing we observe is that we do not have a stable subordinator, but a subordinator. This is because in the case of arrays, there is no a priori choice for the limiting Levy measure of the process. It can be something much more general than a stable law, so something much more general than the law of the form u to the minus alpha we had before, and we will see that indeed we will have cases where this measure is something much more complicated. It will, we will see this today, even if we have time. So this is the basic theorem that we will now apply to study the REM-like trap model. So we remember what that model was. So I will erase everything except perhaps the last theorem. So I will remind you briefly of the definition of the trap model. Where was I? Okay. So application to the REM-like trap. Let me also check time. So quickly, we saw yesterday that the graph, Gn, is the complete graph on the first n integers. To each vertex of the graph, we have attached a positive random variable, tau n. So this is a sequence of IID positive random variables that are in the domain of attraction of a stable law of index alpha. So the probability that tau is larger than u is of the form u to the minus alpha L of u for some alpha in 0, 1, where L of u is slowly varying at infinity. Then on this random landscape, we built a Markov jump process xn. And we did that by specifying the jump chain. This is a discrete time Markov chain. Which simply jumps from x to y. So I will, to simplify things even a little bit more, I will add to my graph self-loops. So that really my jump chain now is in fact a collection of IID random variables. This is the simplest possible model we can. So this is if x and y form an edge of this graph, and this twiddle here will always mean that x and y are nearest neighbors. So, so this is the jump chain, and the mean holding time at a given site I at a given site x is equal to tau x. So we had this picture of a graph, sites, and when the process is at x, it waits there an exponential time of mean value tau x. When it jumps, there is no n. Yes. When it jumps, it chooses to go to its next state with a uniform probability. So the clock process Sn is the total time spent by the process along its trajectory. So it is the sum from 1 to k of the mean holding time at site, j and I times a and I, where these e's are IID, mean 1, exponential random variables. And we are interested in finding sequences, AN and CN, that make the rescaled clock process converge. So I will rescale this. I introduce a sequence AN, which is an auxiliary timescale linked to the jump chain, and a sequence CN, which is the timescale of the process. And I call this SNT. So it's too small, I guess. So this is my rescaled clock process. Now I want to find sequences that make this converge. And this is a sum of independent random variables. So I think we are in a good position to prove convergence using this theorem here. Now, there is just one thing that we must decide. It is a sequence of independent random variables, but it depends on several random variables. It depends on the law of the process xn through the jump chain and these exponentials. And it depends on the random environment through the taus. So we must decide in which sense we want to prove that this converges. Now here, physicists tell us that the result that has the most interesting content from the point of view of physics is a result that is valid for almost all realization of the random environment. So a result that is valid P almost surely in the random environment. So what we will do is fix a realization of the taus of the random environment, apply our convergence theorem with this Z and I, but fixed environment. And then, of course, the aim is to try and prove a result that is valid for a typical choice of the random environment. So let us do this. And the first thing we want to do, and this is the only thing we will do, is study here the convergence of, to check that this condition is verified. The first condition, which is the sequential regular variation condition for our z variables. So let me call this quantity nu and u. So this is an times the probability that tau n, j and I, e and I is larger than u. So this is not difficult to express. This is an exponential random variable. So perhaps you remember the notation I introduced yesterday. I called the probability space of this process omega x f x, and p, calligraphic p is the law of the process x. And for the jump chain, we call the law p, ordinary p. I don't know how to call it. It's the usual squared p. So I want to express this tail here. So I will first calculate the exponential. This is not difficult, and I get that this is the expectation of exponential minus u divided by I am missing my Cn. Yes. So is this correct? No, it is. Yes, it is correct, but written in a stupid way. Okay, so the only thing I did here is calculate the exponential, the probability that an exponential random variable of mean 1 is larger than u Cn divided by tau. And this is not x, of course, this is g and I. And now I'm left to calculate the expectation of this quantity with respect to the chain j and I. But this is simply a collection of independent random variables. This is simply a uniform random variable on Vn. So this is equal to the sum from I, let me call it x equals 1 to n of 1 over n exponential minus u Cn divided by tau nx. So now what I get is a sum of independent random variables, because my taus are independent. There is no n, sorry. And so I know how to calculate a sum of independent random variables. To do this, you can use any concentration result. And I proposed one in the lecture notes, which is a Bennett concentration result, because it's a nice one in the case for IID random variables. And when you apply this concentration result, so you know how you do that, you first calculate the mean value of this quantity, then prove concentration, and then you prove that, and it is not hard to do this, that this converges P almost surely to the measure. Let me just check. Don't want to. Yes. This converges almost surely to a measure nu, which is defined as alpha gamma of alpha u to the minus alpha for all u positive. So this converges P almost surely as n diverges. So the result is that. So I will not check this condition here. It is not complicated. You can work it out in the same way. What really makes this convergence occur here is that the tau is a regularly varying random variable. So we do this the mean value of this quantity is calculated a little bit like we calculated we proved. Well, we just saw how to do this calculation by doing an integration by part. So, so now suppose that the second condition is also verified, and what we then have obtained is that this the clock Sn converges to S infinity, where S infinity is a Levy process with this Levy measure. So a Levy subordinator, where this is a subordinator with Levy measure, so in fact, I'm going just a little bit too fast. So let me do it properly. Because since time is passing, I want to go fast, but when we go fast, we do mistakes. So this convergence here is not always almost sure. So let me write the result properly. So I must distinguish two cases. So up to here, it is correct. But the limit for this sum will, Marcello, can you tell me which time I must finish? Because I have 20 minutes, okay. So we have to prove that this converges. Let us put it aside for a little moment, and let me define timescales. So I will say that diverging sequence Cn is an intermediate timescale if there exists a sequence An such that An over n goes to 0 as n diverges, and An times the probability that tau x is larger than Cn is 1. And I will say that Cn is so this is the definition of intermediate timescales, and I will say that it is an extreme timescale if An over n goes to 1, and the same condition here is verified. So the limit of nu here will be different depending on these two timescales. So let me tell you the result for the intermediate timescale first. So if Cn is an intermediate timescale, then the sequence of rescaled clock processes Sn converges to a limit that I will call S intermediate, where S intermediate is a Levy process with Levy measure nu of u infinity given by what I erased, alpha, gamma alpha alpha u to the minus alpha. And this convergence, so it is convergence of the process in the Scarrod topology in the space of Cadillac path, and it is convergence, this convergence is P almost sure in the random environment if the sequence an satisfies an times log n over n goes to 0 as n goes to infinity. And it is in P probability else. So we have a strong P almost sure convergence on intermediate timescales, except on intermediate timescales that become too close to an, so a bit closer than n over log n, where we only have a slightly weaker result, which is convergence in probability. And this you get when you prove this concentration. It is when you want to prove this concentration, what you get is that you can prove this P almost surely under this condition and in P probability under on complement condition. Okay, so now we saw how to prove this. On extreme timescales, that it's clear that that the nature of the limit must change. So in this case, we do have a stable subordinator as a limit because we get a Levy measure of the form u to the minus alpha for alpha in 0, 1 by assumption. So why must it change on extreme timescales? So here we have that an over n goes to 1. Now if an over n goes to 1, then we have that mu n, this regular variation condition, becomes that this quantity with no scaling must converge. Now, this can happen only if these objects here converge. So let me write this. So on extreme scale, so let me form the rescaled landscape, and I'll call gamma n of x the rescaled variable tau x divided by Cn. X is in Vn. Now if we so this becomes 1, and this becomes the sum of the exponentials of minus u divided by gamma. Now let me form the point measure. Let me call it big gamma n, whose points are the rescaled variables gamma n. Then I can apply my Poisson convergence theorem to the landscape itself. And what I get is that this will converge to a Poisson point process. So gamma k, where gamma is a Poisson point process of intensity measure nu so I'm just applying now the same convergence theorem, but instead of applying it to my clock process, I'm applying it to the landscape itself. So we see that when an over n goes to 1, the regular variation condition becomes n times the probability that Zi, so here in this case, tau x is larger than Cn. And because tau is regularly varying. So perhaps I make a mistake with the constant. So let's say constant u to the minus alpha. So we see that in that case, the regular variation condition tells us that when Cn is an extreme scale, then it is of the size of the maximum of the sequence over our entire random landscape. So the rescaled landscape converges. And using this, what we can prove is that the sequence nu n will converge to the sum of the exponential of these point processes here. But the problem is that this is a weak convergence. This is convergence in P-low in the random environment. And this is not enough for what I want to do, because I really want strong convergence of the clock process. I want here a convergence, an almost sure convergence of the clock process, or if I can get this, a convergence in probability. But this weak convergence is certainly not enough. So what do we do when we have a sequence of random variables that converges weakly, and we want a strong convergence? Then we use a Gayrard representation theorem that tells us that we can find another sequence that has the same distribution as the original sequence, but that converges now almost surely. So, of course, we won't have time to see the proof, so that is the basic underlying idea. In fact, in this case, we can find an explicit representation of the random environment that makes it converge almost surely to now the function that I'm going to write down. So let me just give you the result. Yes, I think it's one more page. So anyway, so on extreme scales, the sequences, both sequences of rescaled landscape and the points of our Poisson point process can be represented on a common probability space. That I will call omega f blackboard p bar, such that on that space, p bar almost surely, the clock converges to S extremo as n goes to infinity, where S extremo is a subordinator with Levi triple 0, 0 nu extremo and Levi measure nu extremal of u infinity given by the sum from k equals 1 to infinity of exponential minus u gamma k. So what we obtain here is that on a probability space on which we can represent our limits jointly, we get almost sure convergence of the clock process to S extremal. Well, now X extremal is not a stable subordinator as we had before, but it is a subordinator with this Levy measure. So we see that now the Levy measure is itself a random measure that depends on the limit of our random environment. So what we get here is a random subordinator. So it is, for those of you who know Cox processes are random Poisson processes. So now if you take a Cox process and you sum the points, you get a random subordinator. So this is what we get here. So the reason why the nature of the limit changes when we vary the time scale is something that can be understood quite easily, because so when you take a time scale that is small enough, so this here is the size of the maximum of a random variable in a set of an random variables. Now, when you take an like n, clearly the size Cn is the size of the maximum of the random variables over your entire state space. So it must be that it starts feeling that the state space is finite, because you can't take Cn larger, but there's no more random variables to be found. So there is a change in the behavior of the process, which we will characterize better in the case when J is really a jump chain, because here it's a rather trivial object, the sum of IID random variables. But the idea is that the process is reaching equilibrium, and then when it reaches equilibrium, it starts filling its invariant measure. This is what happens here. So I will perhaps just tell you, I have 4 minutes or no more? Okay. I will just, I can also do it, I don't know, it's, yes, okay. So we want, the reason why we were studying clock processes is because we want to understand the correlation functions of our dynamics. And I just wanted to give the result that we will use to prove convergence of the correlation function. So I will perhaps need a little more room. So let me erase here. So you remember from yesterday that we started with 2-time correlation functions and 2-time correlation functions of the form pi n that depended on TW, the waiting time, and T, that was the duration of the experiment. And this quantity was defined as the probability that the process Xn TW is equal to Xn TW plus S for all S in 0t. So this is a probability that the process does not jump in the time interval 0t, so TWT. So if 0 is here, TW plus T. This is the duration of the jump. Okay, that's time. And we saw yesterday that this is the probability that the range of the clock does not intersect the time interval TW plus T, where the range Rn is the range. So here it is on time scale Cn. So sorry, I forgot that. And the range is the rescaled. Is the range of the rescaled clock process. So Sn, An, Sn, Sn. Well, it is rescaled. So SNC, C positive. So we were interested in understanding limits for the clock process in order to deduce the limit of the two-time correlation function. And for this, we now need to use our convergence theorem to prove that this correlation function converges. And I told you yesterday that these quantities here, the probabilities that the range of a process does not intersect an interval, is well understood for stable processes. It is well understood for subordinators. And since I have at some point in this class to give you these results, I think I will use the 5 minutes that I have to do it now. So let us here consider this quantity. So let me erase this n. And let me consider the abstract question that I want to know if I have a subordinator. I want to know the probability that the range of the subordinator does not intersect a given time interval, tw plus t. So there are two situations that can happen. So first of all, this question is reminiscent of renewal theory, because this is a question that you all studied in school when you studied renewal theory, and so in discrete time, and you want to know if a renewal item has a lifetime that will straddle over an interval. So it is exactly the same kind of questions that we are asking ourselves here. And from renewal theory in discrete time, we know that there are two situations. Either the items that are being renewed have finite time, or either they have infinite time. In the case of finite time, we get the classical renewal theorem. And in the case of infinite time, we get the Arc-Sine-Law theorem. Now, the same theorems have been proven for the continuous time processes. And I learned them in Jean Bertoin's book, but I don't know to whom I should owe them. So let me say, look up the book. So let me state those two theorems, because these are theorems that we will use. So the first is the classical renewal theorem for finite time. So this is the range of a subordinator with Levy measure that I'll call mu. So in the finite time setting, the assumption is that the mean of the Levy measure is finite. So the integral from 0 to infinity of the tail measure, mu of u du, is some finite number. Then for all t positive, the limit as tw goes to infinity of pi tw and t goes to 1 over m, the integral from 0 to it's the converse, I think. It's from t to infinity of mu infinity du. So this is the classical renewal theorem that tells you that if we send tw to infinity, this quantity becomes time translation invariant. So that's the first theorem. The second theorem is a continuous time version of Dynkin and Lampert's arc-sine law theorem. Arc-sine law theorem. And so it goes like this. So there are two cases. Let us assume first, that we have a stable subordinator. So if the Levy measure nu is of the form constant times u to the minus alpha for some alpha in 0, 1, then this function phi of tw and t is equal to the arc-sine law density at tw plus t. So this ASL function, and this is true for all tw and all t positive, and there's no limit taken here, where ASL alpha of a given u is the arc-sine law distribution function, sine pi alpha over pi, the integral from 0 to u of 1 over x to the 1 minus alpha, 1 minus x to the alpha du. So this is the case of stable subordinators. And in the general case of subordinators, not necessarily stable ones, what we have is that, so assume that the tail of the Levy measure, nu of u infinity, is regularly varying at 0 plus or at infinity. Then as t goes to 0 plus, respectively plus infinity, the quantity pi twt converges as tw converges. So then as tw converges either to 0 plus or to infinity to the arc-sine law density of parameter alpha evaluated at tw divided by tw plus t. So there are two cases that both will lead to a behavior that resembles the behavior that physicists have predicted, that the time it takes for the process to decorrelate will be roughly proportional to tw. So the idea now is obviously to use our convergence results for the clock process and try to use these two theorems for the convergence of these probabilities here, that the range does not intersect this interval, to prove that the correlation functions for the REM-like trap model converge, so either to the arc-sine law density, which will be the case here, and it will also be the case on extreme scales, but taking the limit as time. So perhaps I will write that down properly tomorrow because it's hard to understand. So there will be two cases: convergence to the arcsine law density, which will happen on intermediate scales. On extreme scales, we will be in the case of the finite time renewal. So aging here will be interrupted, except when we take limits as time goes to 0, where we will again get the arcsine law density. That will be all for today.